Section 1.3 is on page 24. It talks about vector equations. And we're going to start with given two vectors. If you want to add those, you simply add the components. And if you want to subtract them, you subtract the components in order. If C happens to be a scalar, and you multiply a vector u by it, you end up multiplying each component or entry. Two vectors are equal if and only if the corresponding entries are identical. So, really quick, if I would like to take given two vectors u plus v, well, u plus v would be 3, 2 plus a 2, negative 1. That would simply be 5 and a 1. And if I wanted to take u minus 2v, well, the same. U is 3, 2 minus 2 times 2, negative 1. You could do this in a couple of steps. You could do it in one step. It really doesn't matter. Just we want to make sure that you get the idea. And you could say that's plus and multiply the negative. You could say minus multiplied just by 2 if you wish. And that will be a negative 4 and that will be a 2. So you're basically saying that's a negative 1 and a 4. So it's really straightforward as far as adding and subtracting. Very close to what we did back when we took trigonometry. That's been a while. Now, something to start looking at. This is really where we want to pay attention and start really looking at this. And the form makes a big difference, especially on the long run. If I am to multiply this, wouldn't this be actually negative 2x1, 3x1, plus 8x2, 5x2, plus x3, negative 6x3, equaling 0, 0. So here we're applying the first properties, multiplying by C, so to speak. And if I combine those, if I add those, wouldn't that be negative 2x1 plus 8x2 plus x3? And wouldn't that be 3x1 plus 5x2 minus 6x3 equaling 0, 0? And write a system of equations equivalent to this. Wouldn't that mean negative 2x1 plus 8x2 plus x sub 3 equals 0 and 3x sub 1 plus 5x sub 2 minus 6x3 equals 0? And how is that? That's by two vectors are equal. I have this vector with one entry, which means that must equal this and this must equal this. Now the question comes along the way, how quickly can you go from this to this? You could do all of these steps, but they're expecting within the next section, I think you're going to start working back and forth between this and this automatically. You're going to start writing that as negative 2, 3 multiplied by x1 plus x sub 2 multiplied by 8, 5 and 1, 6 multiplied by x sub 3 equaling 0, 0. Also, they're going to assume from this you could come up with the augmented matrix directly. Alright, now write a vector equation that is equivalent to the system. A vector equation, well again here it is. So if I take x sub 1, wouldn't that mean I'm going to have a 4, 1 and an 8 right there times x sub 1 plus, isn't that a 1, negative 7, 6 times x sub 2. So they write the theorems in these forms, so you really want to get acquainted with that. And x sub 3, wouldn't you say that is 3, negative 2, negative 5? And wouldn't that equal the 9, 2, and 15? So this is a vector equation. In a couple of sections, we're going to write matrix equation. For now, that's sufficient. And we are going to take this a step at a time. No need to rush, but we need to digest this information. Two ideas that never go away. This linear combination is something that we're going to be trying to figure out all throughout linear algebra. Linear combination means multiples. Given vectors v1, v2, all the way to v sub p, and some r sub n. And these are scalars. We say, if you take these vectors and multiply them by numbers and add them somehow and get another vector, we say that vector is a linear combination of these vectors with these weights. I'll show you what that. I'll show you a couple of examples in a minute. Now, if I look at a vector equation, that's what we just did on the previous example. That's really number 10, and this is the vector equation. Given a vector equation, so a vector equation has the same solution set as the linear system whose augmented matrix. Well, it's very simple. Can't I go from this to augmented matrix? Shouldn't that be the same thing? They should have the same solution, right? In particular, vector v can be generated by linear combination of a sub 1 to a sub n, if and only if there exists a solution. So, if I solve this and I do get a solution, that means b is a linear combination of those by this definition. And if I find no solution, that means that's not a linear combination of those. And here we go. So that's the beginning of some theorems that you really need to pay attention and understand. And this is not only for this section, this is for the next 5 chapters. Everything we do in linear algebra. Determine if B is a linear combination. So linear combination is very hard to find. It's a lot of work, not hard, I should say. They're saying, can you multiply this vector by a number, this vector by a number, this vector by a number to get that? For example, I could say, multiply this by negative 3, this by 1, and this by 1, and add them. Wouldn't 1 plus 0 minus would be a negative 5? But does that work if I multiply this by negative 3, this by 5, and this by 1? Would I get an 11? So I have to find the weight for the whole thing. To really make this simple, we would go for, so this is what they're asking. They're asking is C1 times A1 plus C2 times A2 plus C3 times A3 equal to B. That's what they're asking. And the way it works, you would start with -1, -2, 2, that's C1, 0, 5, 5, that's C2, 0, 2, 8, that's C3, and again there I'll put a line, I put the line augmented matrix. I solve this equation. If I can get a solution, that means there is a C1, C2, and C3 that would work that way. Now I am gonna jump ahead and show you what happens if I do my magic. Multiply row 1 by 2, add it to row 2. Multiply row 1 by negative 2, add it to row. That should be it. And if I take negative row 2, add it to row 3 and here we go. What does that mean? This says 0 C3 equal 2. 0 equal 2. That's not true. There's no solution. If there's no solution, that means this right here cannot happen. Are we getting this? So if there's no solution, we say B is not a linear combinations of A1, A2, and A3. And that's really how it works. So this is the nicest way of figuring things out. It's a bit long. We're going to learn a few tricks to do that differently. And now I'd like to look at this problem as well, number 14, and let's make sure we understand what it's asking. It says, determine if B is a linear combination. I went too far. Determine if B is a linear combination of the vectors formed from the columns of matrix A. Well, think about it. If I take this matrix A, doesn't that mean I could write matrix A as 1, 0, 1, negative 2, 3, negative 2, and negative 6, 7, 5, and 11, negative 5, 9. What does that mean? That means I took C1 times 1, 0, 1 plus C2 times negative 2, 3, negative 2 plus C sub 3 times negative 6, 7, and 5, and I set it equal to 11, negative 5, and 9, and see if I get a solution. Well, what if I told you that if I am to really work this out, this will reduce to 1, negative 2, negative 6, and an 11. This will be 0, 0, 3, 7, negative 5, and I'll get 0, 11, and a negative 2. They're not asking find. They're saying determine if B is a linear combination. We have a solution. This has a solution. And since we have a solution, what do we conclude? B is a linear combination of matrix A. So A, I could write, what's a matrix? It's a list of numbers. Not really, actually, it's an array of vectors. It's a list of vectors. So you could think of those as V1, V2, V3 if you really want. You could put them that way, you could put them that way. Something you really want to get used to, and not to worry, we have plenty of practice to do. Alright. Now, if V1 through V sub P, so those are P vectors in R, then the set of all linear combination, any multiples of those, is denoted by span, and you list them out, is called a subset of Rn spanned or generated by V1 through Vp. That is, the span of V1 through Vp, V sub P, is the collection of all vectors that can be written as a combination of those. Of course, C1 through C sub P, those are called the scales or the weights. I could give you a line span is easy. Take that line right there, V, and any multiple of that, any multiple, 0, if you multiply it by 2, by 3, by negative 1, by negative 2, as long as you are on that line, you are in the span of that line. If you go to 2 dimensions, that becomes a bit trickier. Now, if you take U and V, they span this plane, which means any vector on this plane can be written as a multiple of those. And to show you the span of the rectangular coordinate, the coordinates, this spans 1 dimension. You could multiply that by any number, you'll be on this number line. This right here spans R2. So this spans the reals. If I wanted to span the X and the Y, the two dimensions, I will use 1, 0, and 0, 1. I'm saying no matter which point you give me, any rectangular point, 3, 5, I could say multiply vector 1 by 3, vector 2 by 5, you'll get there. So any point, any coordinates you give me in two dimensions, it's in the span of those two. And if I go for R3, the span of R3 is actually the vectors 1, 0, 0, 0, 1, 0, and 0, 0. If you want to go by coordinates, you could do that all the time. Now, we're going to be playing with span for a while. We're going to build on that. Let's make sure we understand the idea. It says, list 5 vectors in the span of those two. Whatever those are. For each vector, show the weights v1, v2, used to generate the list of the 3 entries. Do not make a sketch. Graphing turned out to be a lot more challenging than we like. So I could say, in the span of those, I could say 0 v sub 1 plus 0 v sub 2. That'll work. Isn't that a vector? Isn't that the 0, 0, 0? Very easy. Multiply this by 0, multiply this by 0, and add them. I could say, take v1 plus 0 v sub 2. That'll work. I could say v sub 0 v sub 1 plus v sub 2. I could say v sub 1 plus v sub 2. So here we're putting 1 there and 1 there. I could say 17 v sub 1 plus 3 v sub 2. That'll work. That's 5 right there. All of these are in the span of those vectors. Now, just to make sure you see this, so basically, AV1 plus BV2, in which A and B are any real numbers, will be in the span. Just to demonstrate, 2, 1, 3 is not in the span. 2, 1, 3 is not in the span. Why is that? Because there's no way of multiplying this by a number and this by a number and add them and make them a 1. That's not possible. So I could multiply this by any number, I could multiply this by any number, I could add them or subtract them any way I want. But I can't add to the entries. I could multiply them by a weight and add them together. Since those are zeros, no matter what I multiply 0 with, I'll get 0. So if this number, any vector with that component not being a 0, cannot be in the span of this vector. In the span of those vectors. And here we're checking. It says, let this be v1, let this be v2, and let this be y, some other vector. For what values of h is y in the plane generated by v1, v2? Basically, they're asking for what values is it in the span. So basically, this is what we're saying. 1, 0, negative 2, negative 3, 1, 8. Let me write that. We're saying, take C1 times 1, 0, negative 2. Even more I'm going to write. Take C1 times V sub 1 plus C2 times V sub 2 equal to y. If you could find such C1 and C2, we say this is a linear combination of that, and therefore it's in the span. What this means, take C1 times 1, 0, negative 2 plus C sub 2 times negative 3, 1, 8. And see if you can get H negative 5, negative 3. This means I could have wrote the augmented. The reason I'm writing this, students had a heck of a time with this last time. So this is saying C1 minus 3C2 equal H. No C1. C2 equal negative 5 and negative 2C1 plus 8C2 equal a negative 3. You're not required to do any of those. I'm just showing you what those are. Negative 3, 1, 8. Right? And if I go by H negative 5, negative 3, and I'm going to put that line. And here I notice if I do the row reductions, 1 negative 3H multiplied by a 2 added to that third row, so here we know that this is already multiplied by a negative 2 and added to the bottom row. And what do we get? We get 1 negative 3H. We get 0, 1, negative 5. And we get 0, 0, 7 plus 2H. So what do we notice? They're asking for what values of H is Y in the plane, meaning it is a linear combination. Are we comfortable with this now? And if you're not comfortable, you could write it. 0 times C2 should equal 7 plus 2H. But for this to work, I must get this to equal 0. Otherwise, there's no way of a solution. How do you get that to be a 0? By letting H equal negative 7 halves will ensure H equal negative 7 halves will ensure there is a solution, and hence Y is in the span of V1 and V sub 2, i.e. a solution. The homework on this section